Welcome. This is a lecture on huckel theory. The topic is covered in your textbook, Chapter 13, Section 8. We use huckel theory in this course just to give you an idea of how computational chemistry got its start. We're going to learn about basis functions through studying this theory, but I want to make it clear up front that it's not a theory that's used an awful lot in any sort of practical way today. We have much more sophisticated models. But it's worth studying because it introduces you to the concepts that the more sophisticated models are built from. So here we go. We're going to do a couple examples, apply butadiene theory to it. We'll do some work by hand, and then we'll do some work in MathCAD to see how you can solve a system like this. So huckel theory is a primitive theory. It only applies to systems that have pi electrons. It treats only the pi electrons and ignores all others. So if you were looking at the butadiene molecule that has 4 carbons, right? And then 2 hydrogens on each end, and there would be 1 hydrogen on each of the carbons in the middle, butadiene with 2 double bonds, right? The butadiene molecule would be represented in huckel theory as just 4 connected atoms. Here I've numbered them, 1, 2, 3, 4. 4 connected carbon atoms, each with 1 unhybridized p orbital sitting on top. So you see them side by side here, the p orbitals. Those are the functions that we're going to put on each of the atoms. Just like when we did hydrogen molecular cation example, we put a 1s orbital on each atom. Here we see we're going to be putting a pz orbital on each atom. And then we're going to let them blend together and see what we get in terms of the resultant wave function and energy for the system. So you see now why we were saying only the pi electrons are being treated here, because we're only using the pi the p orbitals, which go into making the pi system. Huckel theory has 5 basic premises that are behind it. It's how you define the Hamiltonian and solve the secular determinant. And we'll go through these one by one. First one, the atomic orbital basis set consists of just putting pz orbitals on each atom. So we see that in the diagram, and that's listed here. The second item here, alpha, is the self-energy of an electron in one of these pz orbitals. So we're going to be referring to the quantity alpha as a parameter. It just means it's a way of measuring the energy that would be if 1 electron were in one of these orbitals. Beta is another parameter. Beta is the matrix element connecting 2 adjacent Bz orbitals. So we'll see that because the p orbital sitting on C3 is right next to the p orbital sitting on C4, their interaction energy is beta. The fourth item here, non-adjacent Hamiltonian matrix elements are 0. So as we said just a second ago, the p on 3 and the p on 4, their interaction is beta. But the interaction between the p on C2 and the p on C4 would be 0 because they're non-adjacent. Only adjacent carbons will have interaction, and we'll set all of the other hydrogen Hamiltonian matrix elements to 0. Finally, for the overlap terms, the S's in the secular determinant matrix, those overlap matrices are all 0. And so the overlap between one orbital and itself will be 1. So putting that all together here, let's show you what the secular equation would look like for solving butadiene. There are 4 basis functions. Therefore, it's going to be a 4 by 4 matrix. And using these definitions now, we can set that up. You see we've got diagonal elements that are all the same, alpha minus E. That's because the H11 element would be alpha, just like the H22 and the H33 and the H44. Then remember what this equation looks like. Every element is H minus ES. H minus ES. So H is alpha. The S is 1, so that's why we get alpha minus E for all of the diagonal elements. The other elements of the matrix will either be beta or 0, depending on if that particular basis function is next to another basis function or not. So let's go across one row here and make sure we understand all of this. So alpha minus E, that's just due to this first carbon that we see here. Beta, that's the interaction between carbon 2 and carbon 1. They are adjacent, therefore we put beta. Carbon 3 does not interact with carbon 1, so that's why that's 0. Carbon 4 does not interact with carbon 1, so that's why that's 0. So we proceed through the rows all in the same manner. The diagonals are alpha minus E. The off diagonals are either beta or 0, depending on whether we have the carbon being next to another carbon or not. And that's how we fill out that whole matrix. Now, at this point, I think it might be useful to just do some practice with this, right? Before I go on and solve this and show you the results for butadiene, let's take a look at some other molecules and see if you can't construct the determinant matrix using these rules. So the practice that I suggest that we do is available on Canvas. You can download this. But here are 5 practice problems. Well, one of them is already one that we've just done, so you really only have 4 of them to do. But if you want to try this now, ethene, allyl radical, cyclobutadiene, methylene cyclopropene. We're going to do each of those examples. If you're not sure what the structure of that molecule is, you can easily find it. Look it up. The important thing here is to draw the structure and label the carbons, because there'll be, carbon 1, carbon 2, carbon 3, etc. You need to label those so that you know which column and which row of the matrix goes with which atom. But after you've done that, see if you can't construct these matrices, and pause the video, come back, and I'll show you the answers. Well, hopefully you've had a chance to pause the video and try this on your own. Here we're going to go through the answers for these example problems. First one, part A, was ethene. Ethene is just carbon double bonded to a carbon. So the huckel model would just have C1 attached to C2. That would be a 2 by 2 matrix. And it would look like this. X's on the diagonal and 1's on the off diagonal. Now here I'm using a shorthand notation for X, right? We would have, this is the same, let's say, as if we were to put alpha minus E wherever you have X, and beta wherever you have 1. I've made this little shorthand notation by saying, okay, let's define X as being alpha minus E over beta. And then what we can see here is that we've divided through the original matrix by beta and replaced alpha minus E over beta with X. That's how I come up with this shorthand notation. So originally, each X would have been alpha minus E, and each 1 would have been a beta. Allyl radical, let's see what that looks like. Here we have 3 carbons all connected together, label them 1, 2, 3 from left to right. And now I would have x's on the diagonal, right? And then if we go across first row, we would have x, 1, 0. The second row, carbon 2, that's attached to both 1 and 3, so that's why we have 1x1. And then finally for the third row, 0, 1x. Butadiene, here's the way butadiene would look in my shorthand notation. X is on the diagonal, 1's on the off diagonal, just one off of the off diagonal, and then 0's everywhere else. Cyclobutadiene, notice this is the same number of atoms, 4 carbons, so it's going to be a 4x4 matrix, but the matrix is structured differently than in butadiene. The cyclo form, as opposed to the linear form, will have different elements present. You have basically you add in these 1s that appear in the first row fourth element and the fourth row first element. That has to do with closing the ring. So x on the diagonal, 1's on just off the diagonal, and then a 1 here and here, 0's everywhere else. Finally, again, 4-atom structure, methylene cyclopropene. Again, the connectivity will lead us to a different looking matrix than the other 2 4-carbon examples. The thing to pay attention to here in methylene cyclopropene, I chose to put this central carbon as number 1, and then the other members of the ring as carbons 2 and 3, and then I chose the 4th carbon to be hanging off the top here. If you used a different numbering system, then your rows and columns will be jumbled a bit and not compared directly to what I have, but it's an equivalent matrix either way. So check your work on this. There should be very few zeros here, only 4 zeros in position determined by how you did the numbering. Okay, so let's go back now to our butadiene problem where we're going to go through the details of solving it. Now that we've learned how to set up a huckel determinant, and if we divide through by beta and call x the quantity alpha minus e over beta, we have the simplified version of the determinant. And if we were to expand this determinant, because it's a 4x4 matrix, we would get a 4th order polynomial. And it would have 4 roots. And those would be the 4 energies possible for the molecular orbitals of this system. Expanding this matrix and solving it for its roots is something that you could do in MathCAD. I'm going to show you how to do that at the end of this lecture. But I thought for this first example, maybe we'd just go through by hand and see how this works, okay? So I'm going to show you the details about how this matrix can expand into this polynomial, and then we can solve that polynomial to get these values of x. Here we are. So there's the original matrix, and when we expand a determinant, what we do is we block off the rows and columns of the matrix, and we would say, okay, here's the first element, x. That comes over to here. Then if you block off the rest of that row and that column, you have a little 3x3 matrix that's down here. And that's what you multiply x by. So x times this 3x3 matrix is what you see here. Then you go to the next column and you see a 1 here, and you block off the column and row that it's a member of, and what you're left with is a 3x3 matrix that you multiply by 1. And as you combine these together, you alternate the signs. So it would be x times this minus 1 times that plus 0 times this minus 0 times that. I didn't include the ones that have zeros out in front because they, of course, go away. We can do that same sort of expansion in the next step. Just keep the x out in front. What does this become? It becomes x times this little matrix here minus 1 times this little matrix here. And then we'll do the same expansion of this one. And now the last expansion needed are these little 2 by 2s. They're the easiest to do, right? This would just be x times x minus 1. This would be 1 times x minus 0, x times x minus 1, and 0 minus 0. So I've shown that in this line here. So we've got x times x squared minus 1 minus x squared minus 1 minus 0. Combine everything together to get our polynomial in x. It's x to the 4th minus 3x squared plus 1 when we're all done. And we can solve that equation and find these roots. They come out sort of in pairs, plus and minus 1.618, plus and minus 0.618. Let's put that information back into the energy picture for the Huckel theory applied to butadiene. And each of these values of x now represent a different solution to the secular determinant for that set of 4 atomic functions. So that will give us 4 molecular orbitals in the end. We put, this is a general statement, right? You have 4 atomic functions going into a calculation, you're going to get 4 atomic functions, molecular orbitals out of the calculation. And here we see how to take a value in x and convert it into an energy. So what the lowest energy molecular orbital will be the most negative value of x, and its energy will be alpha plus 0.1618 beta. Alpha and beta are negative numbers, so this whole thing will be the most negative energy of the 4. A value of x equals minus 0.618 will turn into an energy of alpha plus 0.618 beta. So you just take the value of x and you plug it in here and make it alpha minus x beta. That's what we're plugging in here, because energy is alpha minus x beta. That's the definition that we used for x to begin with. So these are orbital energy. If we had values for alpha and beta, like I said, these are parameters. Self-energy of the electron in a p orbital is alpha. Beta is the interaction between 2 adjacent p orbitals. So if we had numbers for these, we could actually get numbers for the energy. The butadiene molecule itself has 4 electrons, 4 pi electrons, let's be clear. And so they would fill up these 4 orbitals. The first 2 would have 2 electrons, and the last 2 would have no electrons. That's the neutral butadiene. So, to summarize our results, the total energy for the butadiene molecule would be, add up the orbital energies for those that are occupied. We only have the lowest 2 that are occupied. There's 2 electrons in each, so we would be taking 2 times this energy plus 2 times this energy. And that would give us our total energy that I'm showing here in red. What's the energy according to Huckel theory of the butadiene molecule? Well, it's 4 alpha plus, and then if you add up all of these, 4.472 beta. Try that on your own. Make sure you see where that's coming from. But we've got 2 electrons in the lowest orbital, so it's twice this energy. 2 electrons in the next to lowest orbital. So it's twice that energy. And if we add them all up, we get this. Next thing to do is to go back and use our values of x and solve for what the MOs would look like. So just to remind you, this was the original matrix that we used here. And everywhere we see an x, we will have a coefficient for that row and that column. So if we look across the first row, x, 1, 0, 0, I can turn that into an equation for the MO coefficients by putting in C1x plus C2, and then there's 0, 0, so there's no C3 or C4. Next row, it'd be C1 plus C2x plus C3 plus 0. And that's what I'm showing here. The third row is C2 plus C3x plus C4. And the last one is just C3 plus C4x. That's how you take the determinant equation and turn it into a system of 4 equations where you can solve for the MOs. Now this is an overdetermined system. There are many groups of C1, C2, C3, C4 that would obey this set of equations. And so the way in which we can find at least one solution is to set one of these coefficients equal to 1. So I'm going to pick C2, set it equal to 1, and then find the others in terms of that. So if I put in 1 for C2 in the first equation, I can solve, and I'll have that C1 must equal minus 1 over x. In the same fashion, I can use that result then in the second equation. Plug in minus 1 over x for C1, 1 for C2, and then solve for C3. That's how I end up with this expression for C3. And then finally, for C4, I can use the third equation and solve for C4, and I get 1 minus 1 over x squared. So we've got all of the coefficients figured out at this point because we know the value of x, and we can plug in and get each of these. As I said, that'll give us 4 numbers that will work. In order to normalize the wave function, we want each of these c's, if you square them and add them up, we would want that to equal 1. And so we can actually solve for a normalization constant that would allow that to be true. If you want to see the details of that, I can show you the algebra. I have that available right here. I don't want to take too much time here, but I'm displaying the algebra. If you want to pause the video and look at each step by yourself, you can. But I'm just basically saying, okay, if this is going to be true, what does n have to be? I solve for n, and I get my normalization constant in terms of x. So now, since, again, I know what x is, I know what x is for each of the orbitals. I've already solved for that. That means that I can find what's the normalization for each orbital and what are the coefficients for each orbital. Putting this all together gives us the following results for the MOs according to Huckel theory. And here I've repeated the energy in this column that's coming out of the Huckel theory. I've shown that we've got the lowest 2 occupied with electrons. These 2 are unoccupied. And the coefficients are all, these are the numbers that you get by filling in x for the different coefficient expressions I just showed. So let's try to do a little sketch over here of this orbital. Each of these orbitals will look a little different, and I'm going to pay attention a little bit to the structure of these numbers, the symmetry, right? And then also their relative magnitude. So the first one is has a plus 0.4, then a plus 0.6, then a plus 0.6, then a plus 0.4. So I'm going to have a smaller orbital on the outside, bigger orbital on the inside. And they're all going to be the same sign. That means they're going to be aligned the same way. The second orbital, notice how things change. First of all, the bigger ones are on the outside, smaller ones are on the inside, and they change sign here in the middle so that the ones on C1 and C2 will be lined up, and the ones on C3 and C4 will be flipped. The third orbital has large on the outside, small on the inside, and they're going to be flipped between C1 and C2. They'll stay the same between C2 and C3, and then flipped again between C3 and C4. Finally, the highest orbital one is going to have the larger ones in the middle, and they alternate in sign, so all the orbitals will be flipped. That was the description. Now let's look at what that means in terms of a sketch. Here I've done a sketch by hand that gives a good sense of the relative magnitude of each contributor to the MO. I'm using color to show whether the orbitals are lined up with one another or not. And over here on the right-hand side, I'm doing a figure that could be generated using ChemDraw. It doesn't contain as much information because I haven't made the orbitals size, the relative sizes properly, but I have done the flipping of the orbitals appropriately. So does that match up? Take a look at that. Does that match up with what we saw for the coefficients, what I just described? The lowest energy orbital with 2 electrons in it will be this orbital with bigger contributors in the middle, smaller contributors on the outside, and everything is lined up. That's a bonding orbital. Let's take a look at the next orbital. It has 2 electrons. The smaller contributors are on the middle. The bigger contributors are on the outside. And there's a change in sign in going from C2 to C3. That's sort of a bonding orbital and an anti-bonding orbital, right? It's bonding between the 2 outer carbons because those p orbitals are lined up. But it's anti-bonding. There's actually a node that's going right through this bond between C2 and C3. So it's bonding, but it's also anti-bonding. If you stop for a moment and just consider these 2 orbitals, which are the ones that have electrons in it, this is how Huckel theory is explaining the double bond. This orbital has all carbons connected by a single bond. This orbital has the outer 2 carbons connected by additional bond. We call that a double bond. Now the 2 orbitals that don't have electrons in them, these would be excited orbitals. You'd have to pump energy into the system if you wanted these to be occupied. They have the characteristics that I've shown here. Bonding in the middle here, anti-bonding on the outside, and then the highest orbital is completely anti-bonding because you've got the flip of sign going from each carbon to the next carbon. So we've gone through butadiene by hand. I've showed you how to get the actual numbers out. I've showed you how to do a little picture here. Let's finish up this lecture by showing you how you would do this, not by hand, but just by using MathCAD. It's a lot easier, save you a lot of work in terms of expanding the determinant and getting the and solving for the energies and the orbitals. So I have this document is actually available It's available as a PDF and as a MathCAD document, so you could download either one just to play around with it. If you have an example that you want to do other than butadiene, you could modify this document. So the first thing to declare here is the matrix itself that we've been working with. So I've called that capital M. It's a function of x. I've filled in the x's, ones, and zeros. I can define then the polynomial of x as being the determinant of that matrix. And there I'm showing you. MathCAD is quick to tell us what we already knew about that polynomial. And so we've verified our work. And you can actually factor that, and so you can see what that factors into in MathCAD. That's a useful thing to have available. Remember, we talked about this before. If you want to pull out the coefficients of a polynomial, we'd use the coefs function. Here's how to do that. I'm defining a vector v. V is p of x with the coefficients pulled out. And we see them listed now, 1, 0, minus 3, 1, 0. Those are the coefficients starting with the highest power of x, which is x to the 4th. So that's 1, x to the 3rd is 0, x squared minus 3, x is 0, and then the final x to the 0 power is 1. Now if we take and find the roots of that polynomial, we can say the roots, or I've just called it R. R is defined as the polyroots of V. I put a little negative here just to list out so that the negatives would appear here. The roots are listed. These are the same numbers, recall. These are the same ones that we did when we did this problem by hand. These are the roots of the huckel equation. Each MO would be found by setting these equal to alpha minus E over beta, so that the total energy would be 4 alpha plus 4.472 beta. Just for fun, another thing you can do with Huckel theory is to plot out the polynomial that you get, and you can see that this crosses the x-axis in exactly 4 places. It's symmetrical, and those correspond to the 4 roots that we found here. This is some people like to think of this as another picture of what butadiene looks like. This graphical picture or mathematical picture is what butadiene looks like. There's an alternative way of doing this in MathCAD. I wanted to show you that. Instead, what you can do is if you start out at the top of your document defining alpha and beta as being 0 and minus 1, you can create a different sort of matrix, one where instead of an x you put alpha, and instead of the 1s you put beta, and you can define that the energies to be the eigenvalues of that matrix. There's a function called eigenvals that is available within MathCAD, and it will solve and find you those very same roots that we found before. What's even better about taking this option is that it's a way of getting the MOs. If you take that very same matrix and ask for the eigenvectors, so we'll call this MAT matrix, is eigenvectors of that matrix, it will dump out for you these individual rows and columns. You just have to pay a little bit of attention here to how they map up, right? So the you can sort of see here this first column, all the signs are the same, and so that goes with the lowest energy, which is negative 1.61. Here we've got the second MO, right? You notice the node is in the middle, change in sign is in the middle. That goes with the second number listed here. So when you use eigenvals and eigenvecs, the first number listed here goes with the first column, And the second number listed here goes with the second column. Likewise, third number here is the third column, and then the fourth energy listed here is associated with this fourth column in terms of the MOs. So remember, you're looking at columns here, not rows, to define what the MOs are for each orbital. There is yet another way that MathCAD can solve this. It's using LSolve. And I just want to show you that here. We start out defining this unusual quantity, which is the vector, just putting in small numbers for each element. We can put in the diagonal elements. Here we know the values of the diagonal elements and the off-diagonal elements. And we can solve for these coefficients. We can normalize them and then report out what are the coefficients for that orbital. So that's once we know the values of x, we could do this process for each orbital. Here I'm just showing how to do this for the lowest energy orbital. So I took some time here to give you a sense of Huckel theory. If you have questions, please contact me. This is covered in that one section of the textbook. There's some homework problems assigned, just a few homework problems. And I do plan on the third exam, asking you to do a full analysis of a molecule. In this way, you'll have to use MathCAD to solve it and report out what the total energy is. So you'll want to study this, make sure that you can follow how we've done this solution to this problem in MathCAD, because there'll be one question on the exam that's like that. Yep, that wraps up for this Huckel theory lecture. Hope you enjoyed it. Talk to you later.